So the previous video showed that there is a discrepancy between what we would expect the Earth's temperature to be based upon energy coming from the sun and what is actually observed. And so this greenhouse effect that we're observing in the Earth's atmosphere is due to certain greenhouse gases that can trap this heat that is outgoing from the surface of the Earth. So the different wavelengths we're considering in terms of incoming energy from the sun, UV, visible, and IR. We're primarily interested in this video with the infrared. And so this infrared is being absorbed by CO2, water, and other gases within the atmosphere. And so the surface of the Earth radiates this IR. We mentioned at a maximum wavelength of 10,000 nanometers. And as it's going out and trying to get back into outer space, it gets absorbed by these CO2 and water and other greenhouse gas molecules. And when it does that, it re-emits in every direction. So that is the trapping effect, in that some, yes, some gets re-emitted back into outer space, and therefore it continues traveling in the same direction, but other re-emissions sends it back to the surface of the Earth. And so with enough of these gases in the atmosphere, we create this greenhouse effect. And so this is a good thing, right? This gave us that 34 Kelvin difference between what's expected and what's observed. And that allows us to have a hospitable environment for living things on Earth. But we know that too much greenhouse gases, that would get the Earth's temperature to be too warm. And so what we find is that greenhouse gases absorb primarily the infrared radiation at these wavelengths. And I want to mention too that the absorption of this radiation does not break the molecule. You think about X-rays and UV and gamma rays, those wavelengths will actually destroy the molecule, break the bonds, because the energy that's being absorbed by the molecule is so high. But in terms of the absorption of infrared, it actually causes the molecules to vibrate. And so that's the main topic of this video, is understanding how molecules vibrate and how they absorb the infrared radiation. And so let's consider our greenhouse gases and how they vibrate and how these vibrations absorb infrared radiation. And so these molecules can do different vibrations. They can stretch. So when we go through this modeling of these vibrational modes, think of the bond between the two atoms as a spring. So it's flexible, and it can stretch and it can contract. And so stretching is a very common way in which IR can be absorbed through these stretching modes. But molecules that are nonlinear can also bend. So they can flex out. So this is a nonlinear molecule, and they can flex in. And so this oscillation This oscillation is a vibrational mode. This stretching out and in and back and forth is a vibrational mode. And if you recall from chemistry, is these vibrational modes occur at very specific energy levels. Think about quantum energy levels, very specific levels within the molecule. We can also determine how many vibrational modes a molecule has using these very simple equations. If you have a linear molecule, you can determine the amount of vibrational modes by 3n minus 5. Nonlinear molecules, it's 3n minus 6. The difference between these two equations is based upon the degrees of freedom in which the molecule is able to move. And so that is the reason this one has a 5. It has one less degree of freedom because it's linear. Degree of freedom meaning it can do these motions in just a planar type space, while a nonlinear molecule can vibrate in more of a three-dimensional space. And these equations can be used by putting in the number of atoms within the molecule, that is n. And so we can find the number of vibrational modes using these equations, but not all vibrational modes absorb IR. In order for a vibrational mode to absorb IR, then there must be a change in the electron distribution in the molecule. And so we will do a few examples, and I will hopefully do a decent job explaining this idea, this concept of a dipole moment. We must have a dipole moment in order to actually absorb the IR. So here we see different greenhouse gases and where they absorb the outgoing radiation. And so here's our outgoing radiation, right? Here's our 10,000 nanometer wavelength. This one is actually showing more of an outgoing of about 16 or more. But we see all these little divots taken out of the outgoing radiation. And so this is light intensity heading outward into outer space. And so these divots are where these molecules are absorbing very specific wavelengths, very specific energy levels are associated with these vibrational states within these different greenhouse gases. And so again, let's consider the molecule. And if we think about, again, high energy wavelengths, this is where we actually break bonds. And that's not occurring here. In the visible and ultraviolet, this is where the energy absorbed by the molecule actually causes an electronic excitation. So this means that electrons within the molecule go from a lower energy state to a higher energy state. That gap between the energy states corresponds to the energy in the actual radiation being absorbed, the UV and visible. This is also the case for IR. IR, the energy within the radiation is equivalent to the vibration of the bond between two atoms within the molecule. And so when a certain radiation hits the molecule, it will resonate a certain vibration, but only, again, a certain specific energy is absorbed. So here is another figure showing how these greenhouse gases absorb very specific wavelengths within the electromagnetic spectrum. And so again, these divots here are where these specific molecules, these greenhouse gases, absorb IR radiation. So this figure may be helpful later on when you do your worksheet. So let's look at a few examples and figure out who's a greenhouse gas and who's not. So let's start with oxygen gas. I would expect you all to be able to draw Lewis structures of these gases. I did leave off my electrons here, but I may ask you to draw a true Lewis structure, which includes electrons. So what we have here is oxygen gas, and we see that it's a linear molecule. And given that there's two atoms within oxygen gas, I get the number of vibrational modes to be 1. And so I'm showing that one vibrational mode here. It's just a stretching oscillation. And so the bond can contract or it can stretch, and we have this oscillation. Now, the question is, will this vibrational mode absorb IR? And so when we look at a situation and want to ask the question, will there be a change in electron distribution? You need to consider, where are the electrons in the bond? So they're right here, correct? They're right in the center between this atom and this atom. Well, when it stretches, where is the center of the electron density? Well, it's still right in the middle between the two atoms. And especially since these are the same type of atom, there's no shift in that electron distribution. And of course, oxygen gas is not a greenhouse gas. We didn't expect it to be IR active. And so in this case, we do not see a dipole moment occurring within this vibrational mode. So now let's consider CO2. When we draw the Lewis structure of CO2, we also see that it's a linear molecule. And so we use 3n minus 5, but now we have 3 atoms. So we actually calculate that there's 4 vibrational modes. The first one is a symmetrical stretch. So this is where the oxygens are stretching outward, away from the carbon, and coming back in. So that's symmetrical. And that's different from an asymmetrical stretch. An asymmetrical stretch is where you have, say, one oxygen going towards the carbon, the other one stretching outward, and vice versa, back. And so when we look at the symmetrical stretch and we ask ourselves whether we're getting a dipole moment, again, if you think about where the electrons are within the molecule, the electron density where the center is, if it stretches outward and back, the center of that electron density is not changing. It's being stretched out and then being contracted, but the center of it stays the same. If you consider the asymmetrical stretch, though, you can imagine that you're getting a shift back and forth. The center of the electron density is shifting to one side and then the other. That would create a dipole moment. This vibrational mode, the asymmetrical stretch, is IR active. So because the vibrational mode actually shifts the electron density, the electron distribution, that means that IR radiation will be absorbed. We have two more vibrational modes. They're both bending and they're identical, but they are different in that one is in, say, an XY plane, the other one is in a, say, a YZ plane, depending upon your coordinate system. And so they too are both IR active. If you consider the bending of this molecule, you're going to change where the center of the electron density is. The electron density or distribution will shift, and that allows for a dipole moment to occur upon the absorption of the IR radiation. And so for CO2, we have 3 of the 4 vibrational modes being IR active, and we have 2 bending modes, so they actually absorb most of the IR leaving the Earth. So this is the culprit in terms of climate change. And last, let's look at water, also a major greenhouse gas in the gaseous form, not in a condensed form like a cloud, but actual water in the gas phase. We have a nonlinear molecule now. We have 3 atoms in water, so we get 3 vibrational modes. We get the asymmetric stretch, we get the symmetric stretch, and we get some bending. And so we see the asymmetric stretch, that's where a hydrogen is moving away. At the same time, the other hydrogen is coming towards the oxygen, and it oscillates in this fashion. Again, we're getting a change in the dipole moment upon absorption of the IR. We also see the symmetric stretch, and we see a bending stretch where the hydrogens are moving closer to each other and then farther away. All of these change the center of the electron density and are all IR active. One thing to note is that water is a very efficient greenhouse gas, 10 times that of CO2. And this is an argument that's used by climate change deniers, saying that CO2 is not an issue. It's at such a low concentration, and water is by far the most efficient and numerous in terms of in the atmosphere of all the greenhouse gases. So what's your point? Water is the issue. Climate change is not being caused by CO2, period. Well, that is somewhat of a true statement that water is the more abundant greenhouse gas, and it's very efficient at doing so. But what they leave out is that the concentration of water in the vapor phase is constant over the Earth. It has not changed in the last 250 years. It has not changed in the thousands and thousands of years. It remains constant. So even though it allows us to have this greenhouse effect, which again is a good thing, the thing that has changed and the gas concentration that has accumulated in the last 250 years is CO2, and that is the culprit with respect to what we're seeing in terms of increased temperature on Earth. So we also have these other gases that we'll consider in the next video. So the next video, we will look at potency and also positive and negative feedbacks with respect to different physical and biogeochemical changes that occur.